In the previous video, we saw a few different ways to write strong oxidizing agents. We saw chromium trioxide in water, we saw chromic acid, H2CrO4, and we saw sodium dichromate or potassium dichromate. And what I want to show you here is that these are really all the same thing. These sort of interconvert between each other. So I want to show you how that happens, so that these aren't just random letters and numbers you're memorizing, but you can see conceptual connections between these. Chromium trioxide looks like this. You have a chromium with a double bond to oxygen 3 times. Now if you're looking at this, it should look a little strange. It may look a little strange. What you'll notice is that there are 2, 4, 6, 8, 10, 12 electrons around the chromium. So why? I thought there had to be 8. How is there more than this? Or isn't there only 8 electrons around an atom? The reason why chromium can have more is because it has d orbitals. So the rule for 8 electrons, that's coming from the types of orbitals. You have one s orbital, and then 3 p orbitals, the py orbital, the px orbital, and then the pz orbital that's sort of coming out and going away from you. Each of those orbitals can hold 2 electrons. So 2 plus 2 plus 2 plus 2, that's 8 electrons. So for something like carbon, which only has s and p orbitals, it can only have 8 electrons around it. Something like carbon or nitrogen or oxygen, anything in the second row on the periodic table. And that's mostly what we deal with in organic chemistry, so we see stuff with 8 electrons around it. But if you have d orbitals, you can fit electrons into those d orbitals. And the d orbitals look a little weird, but there's one that looks like a p orbital that has a hula hoop going around it, or there's another one that's like 2 p orbitals that are crossing each other. So whatever, those can hold more electrons, and so you can start to fit more electrons around the atom. And that's the case for chromium. If you remember from General Chemistry 1, on the periodic table, there are blocks. The block on the left here is the S block, the P block, and the D block is in the middle. Way at the bottom you had the F block. So elements that are in these sections have these orbitals filled. And you'll know that you have the d orbital, that elements have a d orbital, because they'll be at least in this row down here. At least in that row where you start to get this valley area of electrons. And so chromium is in this area, that transition area. They're called the transition metals. You're transitioning from the left to the right side of the periodic table. And so chromium is there, and so it has those d orbitals, so it can have more than 8 valence electrons around it. Okay. So that's chromium. Now, we're putting chromium in water. So you have chromium, we're going to have water. How do these things react? How do I know, you say? Why don't you show me, and then I'll tell you later. How could you know, if you've never seen these before, how would you know they react? And the way you could do that is by identifying the charges. If you ever get stuck, if you ever say, I have no idea how this reacts with itself, what this becomes, how this behaves, remember that 95% of organic chemistry is opposite charges attracting. So here in the water, oxygen is very electronegative. It pulls electrons to itself, becomes slightly negative. The hydrogens lose those electrons and become slightly positive. In the chromium trioxide, oxygen's very electronegative, pulls electrons to itself, becomes slightly negative, and the chromium loses electrons to all 3 of those. Not just because the oxygen is very electronegative, but also it's a metal, and metals lose electron density. We've seen that in our reducing agents, sodium borohydride, lithium aluminum hydride, and we've seen that in Grignard reagents with magnesium. Okay, so now that you've drawn these in, if you ask the same question, how do these react, hopefully it seems a little bit fairer of a question. Opposite charges attract. This negative oxygen is going to be attracted to that positive chromium. So these electrons will swoop in, attack the chromium. The chromium, if a new bond is coming in, one of the bonds on the chromium is going to have to break. It's going to be one of the pi bonds. Now it could be on any of those double bonds to oxygen. I'm going to use the one sort of to the right. The pi bond breaks there, the electrons go onto that oxygen. Now that oxygen already has 2 lone pairs, so it's going to have 3 in our new structure in just a second. Okay, so we still have that one chromium. We still have 2 double bonds to oxygen intact. On the right side, will have a bond to an oxygen, but just one, right? The second one broke and became a third lone pair on this oxygen. If oxygen has 3 lone pairs in one bond, it has a full negative charge. On the opposite side, the chromium is going to bond to the oxygen from the water. That oxygen still has the 2 hydrogens on it. And so that oxygen, which has 3 bonds, will have a full positive charge. Now notice, we're getting closer to this chromic acid, H2CrO4. In fact, we already have all of those elements on the molecule. H2, Cr, O, 1, 2, 3, 4. Right, so we kind of already have this, except this is not stable. And you can tell it's not stable because you have these positive and negative charges. So to stabilize charges, you do proton transfers. If something has a positive charge, then you take away an H+, and that brings the charge down to 0. If something has a negative charge, then you add an H+, and that brings the charge up to 0. So proton transfers can stabilize charges. Now those proton transfers are almost always mediated by water. And this is something you'll notice a lot in this course and also in biochemistry. So if you have water, the oxygen there is slightly negative, hydrogens slightly positive. And notice in this molecule, the hydrogens are slightly positive. Now that's because the oxygen is pulling electron density to itself because of its electronegativity. But also it has a full positive charge, and that attracts electrons even more. So the hydrogens here are really losing a lot of electron density. They become slightly positive. And a water molecule can swoop in. The oxygen can pluck it off, can rip off one of those hydrogens. The electrons can snap back onto the oxygen to stabilize the positive charge there. So notice this is a proton transfer. We're taking this H+, that proton, and we're moving it onto water. So what we have at this point is this lone pair will turn into a bond to this hydrogen. That oxygen has 3 bonds now, so that has a full positive charge. That's H3O+, hydronium, classic acid. And this now has the electrons from the bond on it, this oxygen, so it doesn't have that charge anymore. Okay, so we did a proton transfer, and you'll notice that this molecule is more stable than it was before. Before it had 2 charges, and here it doesn't, it only has the 1. And we can stabilize that charge by doing another proton transfer. So the oxygen here is pulling electron density to itself, both because it's really electronegative and because it has this positive charge that's attracting the electrons. If the electrons go onto the oxygen, they're going away from the hydrogens, so the hydrogens have a slight positive charge. And this negative oxygen, as it whirls around in the galactic mosh pit that is this solution, this oxygen can swoop in, attack that hydrogen, the electrons snap back onto the oxygen to stabilize that positive charge. And so this is another proton transfer. Notice what we have at the end of this. We have our H2CrO4 chromic acid molecule. And then we have water. Right? Water's floating around. Okay, so notice how this chromium trioxide and water mixture here, that chromium trioxide and water mixture produces H2CrO4 chromic acid. And this is an acid. The reason why it's an acid is because it can give away an H+. The electrons onto the bond could snap back onto the oxygen. It would give it a negative charge, and that negative charge can be stabilized over all these atoms through resonance, right? Remember, this is an allylic lone pair, so it could exist in a p orbital that's parallel with the p orbitals that are making these pi bonds. And so then it can spread out over all those atoms and stabilize the negative charge, allowing the H+ to get away. So this is an acid. Okay. Next. Also, in this mechanism, notice what took a lot of time and space was just doing these proton transfers. But conceptually, these are really simple, right? You're taking an H plus off of here, you're putting an H plus onto there. Conceptually, that's not a difficult thing to follow, a difficult story to follow, taking an H and a plus sign off, adding an H and a plus sign. But it takes some time, and it looks complicated. It takes time to write it out, and it looks complicated looking at it. But notice this is really a story of a nucleophilic attack and just a couple proton transfers to stabilize it. Okay, so we've built this connection between these two. Now let's build a connection with this and the sodium dichromate and potassium dichromate. So what'll happen here is when I draw, we often just draw one molecule, but of course you never have one molecule. Every time you exhale, we're galactically large. Every time you exhale, you breathe out more stars than there are, you breathe out more stars. Every time you exhale, you breathe out more atoms than there are stars in our galaxy. If you go to the beach, the next time you go to the beach, imagine instead of water, you have blueberries from the bottom of the ocean to the top, not just in the Atlantic Ocean, but in every ocean across the whole Earth. Imagine the number of blueberries you would need to fill those spaces up. That number of blueberries is smaller than the number of molecules of water in one drop of water. So here we just draw individual molecules, but really what they are symbols for whole galactic populations. So if we ever have one chromic acid molecule, we're going to have at least one more present. So let's say you have these multiple chromic acid molecules. One of the things that can happen is that the oxygen on one, which is slightly negative, could smack into and be attracted to the hydrogen on another, which is slightly positive. And so it can sort of attack it, send the electrons onto the oxygen. So we're doing a proton transfer here. And this is something that could easily be undone. So I'm going to draw these equilibrium arrows, but it could happen. It's something that could happen, even if it could also be undone. So this hydrogen is going to move over. It's going to be on this oxygen, which now has 3 bonds and a full positive charge. And then these electrons will snap back onto the other oxygen, and that'll have a full negative charge. Okay, so this is what we have for now. Now to simplify things a little bit, just conceptually, I'm going to treat this next step as an SN2 reaction. Now this oxygen has negative, it can act as a nucleophile. Chromium, as we've seen, is a metal, so it loses electron density to all of the very electronegative oxygens around it. So the chromium is slightly positive, and this can attack the chromium and kick this water molecule off. So I'm treating this sort of as an SN2 reaction. That's not ludicrous. I mean, this chromium is really crowded, but it's not completely ludicrous because chromium is really big, and that means that all of these groups are being kept at arm's length. So even though there is a lot of stuff around the chromium, the bonds are longer, the atoms are held further away because the chromium is a relatively big atom. Remember, atoms get bigger as you go to the left and as you go down on the periodic table, the opposite trend for electronegativity. So, and that should make sense because if you have a nucleus with a bunch of positive charge, electronegativity is how much that attracts valence electrons. If it attracts them a lot, well, then the valence electrons get closer to it and the atom gets smaller. So the more electronegative an element is, the smaller it is. So the atoms get bigger as you go down and to the left, as the electronegativity gets smaller. Okay, and what that means in terms of these molecules is that the nuclei are further apart, right? Because when we talk about an atom, we say the atom gets bigger. What does that mean? If an atom were the size of a football field, the nucleus would be the size of a marble. The electrons would be smaller than specks of dust. So really, when we say the atom gets bigger, it means there's going to be more space between this nucleus and the nucleus of anything bonded to it. That extra space gives an opening for a nucleophile to attack. Okay, So let's imagine that happened, this happens, and what we get next, what we would have next is these electrons would go onto that oxygen, and that would leave as a sort of great leaving group, water. And then this oxygen here would connect to the chromium. So now we have something that is really similar. We're definitely getting closer to the reagent that we wanted to describe, sodium dichromate or potassium dichromate. Notice this, Cr2O7. Cr2O7. Here we have Cr2 and then O, 1, 2, 3, 4, 5, 6, 7. So Cr2O7. Notice also that the hydrogens on the ends are really acidic. Right? These hydrogens can be ripped off because if they leave, the electrons would become a lone pair on this oxygen, and they'd be allylic to the pi bonds here. Now, if that doesn't make sense with the allylic lone pairs, I strongly encourage you to go back and watch the videos on resonance and the resonance patterns of allylic lone pairs. So you can either treat this with sodium hydroxide or potassium hydroxide. Let's say we treated it with sodium hydroxide. Sodium hydroxide is an ionic compound. It's held together through charges. The sodium has a full positive charge. The oxygen has a full negative charge. The sodium often is there just to stabilize the oxygen, and when you put it into solution, it sort of diffuses away. The oxygen in the hydroxide can swoop in, steal the slightly positive hydrogen here, and send those electrons back onto the oxygen. Now, it can do that once on this hydrogen, and it can do it twice on the other hydrogen. So if you add a whole bunch of sodium hydroxide molecules, what you end up getting, what you end up having is a full negative charge on each of these oxygens, because their hydrogens will have been ripped off, and then the sodiums that have been floating around can sort of counterbalance that charge. And so you have Na2Cr2O7. So sodium dichromate. So you'd have two sodiums. You'd have two chromiums. And you'd have 7 oxygens. So 1, 2, 3, 4, 5, 6, 7. So sodium dichromate. If you had used potassium dichromate, the same exact thing would have happened, but you would have had potassium there instead of sodium. And so that sodium dichromate, Na2Cr2O7, was that last example. And if you use potassium hydroxide, you can make that potassium dichromate. So you could see how all of these really interconnect and can be interchanged for each other. So when you see one, it's going to accomplish the same thing as another, because they can all turn into each other.